I used to give talks in English, so today I'll be giving the talk in English. Okay, so I'm a professor at UC Berkeley in computer science, and also I'm the founder and CEO at Oasis Labs. So today I'll talk about the Oasis, privacy-preserving smart contracts at scale. As we all know, data is the new oil. From this data, it can help us to extract valuable insights and help us to make important decisions. However, as we also know, that a lot of this data is really sensitive. For example, including data in healthcare, financial services, and IoT. As we handle the sensitive data, there are many security and privacy challenges. For example, we continue to see examples of really large-scale data breaches in companies where attackers steal sensitive information of hundreds of millions of users. And also at the same time, a lot of this data is being siloed, it's being locked up because the data is very sensitive and there's no sufficient security and privacy protection technologies to help us to, on one hand, analyze the data, and on the other hand, protect the privacy of data. And hence, a lot of data, for example, in healthcare and many other domains, are being locked up, and it's difficult, for example, for medical researchers and others to use. And also, at the same time, we are seeing that users are losing control of their data, as evidenced in the recent examples of Cambridge Analytica example and others. So at Oasis, we are developing a new technology for building privacy-first cloud computing on blockchain with a unique set of capabilities and properties. First, we hope the platform is designed to protect strong security and privacy protection. And second, it's designed to provide high performance, in particular to enable scalability for real-world applications ranging from games to machine learning. And also, in particular, we provide a unique vertical framework for privacy-preserving machine learning and data analytics. And the platform designed to achieve all this with decentralized trust without relying on any central party. So first, let me give you a motivating example how this kind of technology can help us solve important problems. And let's look at the example of fraud detection. So today, banks need to solve fraud detection. And for example, as they give out loans, they need to be very careful about fraud. But today, how the fraud detection is done is typically that each bank only utilizes its own data to build fraud detectors. However, as we all know, for example, with machine learning, typically, the more data you have, the more valuable and the better the model can be. And hence, it would be much better for the different banks if they could somehow pull their data together to build one fraud detector utilizing all these data from different data sources. However, this is difficult to do today for a number of reasons, in particular for privacy concerns, and also, for example, for misaligned incentives between different entities. So with the blockchain technology, in particular, with the privacy-preserving blockchain technology, we can provide a new solution to this problem. In particular, we can develop a smart contract, in this case, a fraud detection smart contract, on top of the blockchain, where the different banks can contribute their data to this smart contract. And the smart contracts can then utilize the data from the different data sources to train and build one fraud detection model. In this way, it can help significantly improve the fraud detection efficacy for different banks, and hence can really benefit each entity. However, to really enable this application, we need to address a number of important challenges. So first, a lot of this data is really sensitive. And And as the sensitive data is being computed on the different workers on the blockchain, we need to be really careful about protecting the sensitive data during the computation process. And second, the fraud detection model, the computation output, can also leak sensitive information because after all, it's computed using sensitive data in the first place. And also, all this is big data and heavy compute. And hence, we really need to enable much greater scalability for the platform than what we currently see in today's blockchain platforms. So at Oasis, we are developing a core technology, a privacy-preserving smart contracts at scale to address these problems and enable the kind of applications that I just mentioned. So again, one of the key primitives that our platform provides is what we call privacy-preserving smart contracts. The smart contract runs on top of the Oasis blockchain platform with a set of unique capabilities and properties. First, it enables automatic enforcement of codified privacy requirements. In this case, the privacy policies are encoded as code in the smart contract and automatically enforced on the Oasis blockchain platform. And this is achieved without relying on any central party. And also, the platform is designed to scale to real-world applications, including data analytics and machine learning. And another really important goal of the Oasis platform is to really design and develop the technology to make it easy to use for developers, to make it easy for them to build privacy-preserving applications without needing to be a security or privacy expert. To enable this, let me now give you a little bit more details about the technical components that goes into the Oasis blockchain platform to enable the privacy-preserving smart contracts at scale. So first, as we look at the blockchain platform, there are essentially two layers that we can look at. One is the platform layer, and the other one is the application layer, like the smart contract that runs on top. So first, at the blockchain platform layer, we develop technologies for confidentiality-preserving smart contract execution to protect the security and privacy of data and compute during the computation process. Second, at the application layer, in the smart contract framework, we enable privacy-preserving analytics and machine learning to protect the computation output from leaking sensitive information about the input. And third, at the platform layer, we design and develop new blockchain platform architectures to enable scalable smart contract execution, and in particular, to enable scalability for complex smart contract execution. So now let me tell you a little bit about each one of these technical components. So first, let's look at the confidentiality-preserving smart contract execution. As we execute the smart contract, the typical workflow is the user sending the inputs, the request, to the smart contract, and then the smart contract executes based on the input, and then does the state transition from the old state to the new state. However, as we want in most today's blockchain platform, the data and compute, they are all public, and hence they can only be used for limited use cases. Whereas for applications, for example, in healthcare and financial services, as I mentioned, they often need to deal with the really sensitive data, and hence we need an approach to provide confidentiality protection during the smart contract execution. So in this case, the inputs are the requests will be in encrypted form, and also the states of the smart contract will also be encrypted and stored in an encrypted form. And also the smart contract in this case will execute using the encrypted inputs and also perform the state transition. And the important aspect is that even though the requests and the states are all encrypted, we still want to ensure that the smart contract execution is correct and be able to provide a proof of correctness. In the Oasis blockchain platform, we utilize secure computation techniques to enable confidentiality-preserving smart contract execution, to protect the smart contract execution process from leaking sensitive information. And in particular, in order to achieve this, we utilize secure computation techniques. The goal of secure computation is to protect the computation process from leaking sensitive information. And there has been a lot of work in this space. And there are two main approaches in this domain. One is to utilize secure hardware. The advantage of secure hardware is that the performance is very good. It's oftentimes close to native computation, and they can support for general purpose computation. The other type of approach is utilizing cryptographic-based techniques, such as secure multi-party computation, or even fully homomorphic encryption. The challenge for this type of approach is that the performance overhead typically can be very high. It can be orders of magnitude performance overhead over native computation. And hence, it can only be used for limited use cases. In the Oasis blockchain platform, we utilize a combination of these different techniques depending on the requirements and the use cases of the smart contracts and the developers and the users. So here, let me talk a little more about the secure hardware. So secure hardware-based approach essentially try to use a combination of software and hardware capabilities to together provide a fully isolated execution environment for the program, or in this case, the smart contract, running inside this isolated execution environment. And we call this isolated execution environment trusted execution environment or secure enclave. And as we run the smart contract inside the secure enclave, the outside operating system and other application processes won't be able to modify what's running inside, and also won't be able to access what's running inside. And hence, the secure hardware helps provide the integrity and confidentiality for the smart contract execution. And also, the hardware provides a hardware-based capability called the remote attestation, which allows a remote verifier to remotely verify what has been running inside the secure enclave and its initial state, and hence provides a proof of correctness for the execution of the smart contracts. In our earlier research project, we are the first to develop confidentiality-preserving smart contracts by combining smart contracts with secure hardware. And also, we provide formal security proofs for the properties and the security that we provide. By combining secure hardware and smart contract execution and blockchain, we can marry the two and try to get the best of both worlds in terms of the properties and capabilities that they provide. Secure enclave not only is important for enabling confidentiality-preserving smart contracts, and hence important for blockchain, it also can serve as a strong cornerstone security primitive for building security applications in general, given its strong security capabilities. In particular, it can provide a platform for building new security applications that couldn't be built otherwise for the same practical performance. All the different hardware manufacturers have recognized the importance of building secure hardware, and hence, over the years, they all have developed different solutions. However, all these commercial solutions are closed source. In collaboration between Berkeley and MIT, we also have been developing a new secure hardware, an open source secure enclave called Keystone. challenges in secure hardware. So for example, how secure can it be? And what their models? And what would you entrust with secure hardware? Your Bitcoin keys, financial data, or health data? And the ultimate question is, can we create truly trustworthy secure enclave as a cornerstone security primitive that's widely deployed to enable secure systems built on top? If we can really do this, then we can usher the entire community into a new secure computation era. So what is the path to building trustworthy secure enclave? So first, we need to have an open source design and implementation. Open source helps provide the transparency that's needed for the entire community to come together to analyze and verify the security and correctness of the secure enclave. It has to enable high assurance. And also open source helps build a whole community. Also, ideally, we would like to provide a formal verification for the open source design of the secure enclave. And also we need to ensure secure supply chain management. Towards addressing these challenges and towards the goal of building an open source trustworthy secure enclave, again, in collaboration between Berkeley and MIT, we have been developing a project called Keystone for building open source secure enclave. And we plan to have a first release of some key components this fall. So Keystone is an open source secure enclave that's designed based on the RISC-V architecture, providing strong memory isolation and other number of important properties and capabilities. RISC-V is an open source RISC architecture that has been developed at Berkeley and also has seen broad industry adoption. The RISC-V Foundation has over 100 members from industry. And also recently, we've organized the first workshop on building open source secure enclave, bringing together leading experts and researchers from academia and industry, with the goal of together building a community for building open source secure enclaves. So that's the first component, how by utilizing a combination of secure hardware and cryptographic-based techniques, in the Oasis blockchain platform, we enable confidentiality-preserving smart contract execution. Next, let me briefly talk about the second component, privacy-preserving analytics and machine learning. So first, let's look at a concrete example. Why do we need to worry about privacy and security of data as we do data analytics and even machine learning? So in this case, in our recent work in collaboration with the researchers from Google, we set out to explore some important questions. In particular, in deep learning, do neural networks actually remember the training data? And if yes, can attackers actually extract the secrets in the training data from just simply querying the learned models? Here's one example of the case study that we performed. In this case study, we trained a language model from an email dataset called the Enron email dataset. A language model is a model where given a sequence of characters or words, it will try to predict the next sequence, the next character, or the next word. This Enron email dataset contained actual users' credit card and social security numbers. So we show that by developing new attacks, an attacker, by just querying this learned language model, can actually extract the original user's credit card and social security numbers embedded in the original training data set. And this is an example demonstrating that even as we do machine learning or even deep learning, we need to be very careful, taking the right precaution to protect users' data's privacy. So luckily here, we actually have an effective defense mechanism. Instead of learning a vanilla deep learning model, instead we can learn a differentially private deep learning model in this case. And our work showed that in this case, if we learn a differentially private language model, it will still achieve very good utility. The utility won't actually be much different. And then at the same time, the differentially private language model can significantly enhance the protection for users' privacy, and essentially our original attacks won't actually be effective. So differential privacy is a formal notion of privacy. It's essentially, so at a high level, differential privacy essentially says that if an algorithm or a function is differentially private, that means that as you compute this function over two neighboring datasets, where one dataset only has one data point that's different from the other datasets, then the output of this function computed from these two neighboring datasets will be almost identical, will be very close. And hence, at high level, this explains this gives the intuition that a differentially private algorithm or function can actually help protect users' privacy, because now even the attacker cannot tell whether the user's data point is used in the computation or not. In our work, we have developed new frameworks for privacy-preserving data analytics and machine learning. And our framework essentially can automatically enforce the desired privacy policies, including differential privacy, for data analytics and machine learning pipelines. And some of the technology that we have developed has already been deployed at places like Uber. So together, by combining confidentiality-preserving smart contract execution and privacy-preserving data analytics and machine learning, we can enable privacy-preserving smart contracts. Now let me just talk very briefly about our approach for scalable smart contract execution. So we hear a lot about scalability, including at this event. But however, here, one thing I want to emphasize is that most of the conversation when people talk about scalability is mainly about scalability for high transaction throughput from payment transactions. But however, in order to support the kind of applications that people actually want to build on top of a blockchain platform, we actually really need to enable scalability much more beyond just high TPS for payments. In particular, to enable scalability for complex smart contract execution, such as smart contracts that can even include data analytics and machine learning. At Oasis, we developed a new blockchain architecture to enable scalability for complex smart contract execution. In particular, utilizing what we call separation of execution from consensus. A smart contract platform, a blockchain platform essentially has three key functions, including consensus, storage, and compute. Most of these blockchain platforms actually bundle these together, and that's one of the main reasons also that make them difficult to scale. In the Oasis blockchain platform, we actually decouple these three key functions. So we have separate consensus layer, storage layer, and compute layer. And hence, we separate the execution from consensus. In this way, each layer can scale independently, and also each layer can improve and evolve independently as well, making the whole blockchain platform much easier to improve and evolve. And also, we use verifiable computing to ensure that the blockchain platform also achieves the same level of security and integrity. In particular, the consensus layer orders the transactions, the compute layer does the computation, and then the consensus layer verifies the correctness of the computation. And they will utilize different approaches for verifiable computing. So to summarize, in Oasis, the Oasis platform does not rely on secure hardware. And in particular, its integrity and scalability does not depend on secure hardware at all. Its scalability comes from separating execution from consensus, and we utilize verifiable computing to achieve strong security and integrity. And the Oasis platform provides a unified secure computing framework by combining secure hardware and cryptographic-based techniques to enable developers to leverage and enjoy the state-of-the-art secure computation techniques, and also provide choices and flexibilities for developers and users to provide options that are best suited for their applications. And also we hope that with the open source secure enclave design development, together with the community, we can provide a shared foundation for secure computing in the future. So finally, let me just give you one example of a dApp developer that a dApp developer is building on top of the Oasis blockchain platform. It's called Kara, a privacy-preserving tokenized data market for medical data. As we all know, the medical data is often locked in data silos. So the goal of this application is to incentivize doctors and patients to share data and improve medical research.
Yes, just Wally, so splendid this first speech. Maybe you will have just 2 minutes, okay?
No, I'm almost done.
Okay, thank you.
So in this, with the Kara application, the users and patients can upload their medical data to the Oasis blockchain platform, and the medical data will be stored in an encrypted form. And a medical researcher can utilize the primitive of privacy-preserving smart contracts provided by the Oasis blockchain platform. In the smart contract, the medical researcher can include machine learning, include code for training machine learning models and for serving machine learning models. And the smart contract can also specify terms of use. For example, it can specify that the data will only be used for training machine learning models and for training a privacy-preserving machine learning model in the smart contract. It will not be used for anything else. And also it can specify how users will be compensated for contributing their data to the smart contract. If a user agrees to the terms of use, the user can then contribute data to the smart contract. And as the smart contract collects enough data, it will then start training the machine learning model, and then the medical researcher will then can then evaluate the effectiveness of the trained machine learning model. As you can see, in this approach, it can significantly reduce the friction for medical researchers and pharmaceutical companies to get access to medical data and train machine learning models, and to help find better cures for diseases.